Hello guys and welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today, problem around dynamics, the idea of relating velocity, acceleration, position, just like the ones we've done before in the channel. If you haven't checked them out, you can look here in the corner. We'll leave some cards for the previous problems. There's really nothing that is much different on this one here. The problem statement reads, a ball is dropped from a boat so that it strikes the surface of the lake with a speed of 16.5 meters per second. While in the water, the ball experiences an acceleration of a equals 10 minus 0.8 velocity, or 0.8 v, where a and v are expressed in meters per second squared and meters per second respectively. Knowing the ball takes 3 seconds to reach the bottom of the lake, determine the depth of the lake and the speed of the ball when it hits the bottom of the lake. All right, so what's going on here? This lovely gentleman here is dropping a ball. When he has it in his hands, the velocity is 0. It's stationary. Then he drops it, and it acquires the velocity all the way until it hits the surface of the water. And we know that exactly at this point here, we have a velocity of 16.5 meters per second. Now, what's going to happen from this point onwards? It's going to continue to go down, right, down the lake, all the way until it hits the bottom of the lake. So it's going to continue on this trajectory all the way until it hits the bottom of the lake. What do we know about this? Well, we know two things. We know that it takes exactly 3 seconds from it to leave the surface of the water and reach the bottom of the lake. We know this happens in 3 seconds. And we also know this ball is subject to an acceleration that respects the equation 10 minus 0.8 v, right? So note that this is telling, right? Because 10, that will be, approximately the acceleration of gravity. And then we have something that is countering gravity, let's put it that way, right? So buoyancy force is acting. The buoyancy forces are increasing as the velocity is increasing, all right? So there is a given point in which when the velocity, the acceleration due to this buoyancy effect is going to be the same as the one due to gravity, again, assuming this is gravity by itself, and the ball is not going to go up or down, it's going to stay stationary in the water, right? Apparently this is not the case here, because right here it is touching the bottom, so this lake would have to be deeper for this to happen, but as is, if it was deeper, then this would stay stationary at some point. But as is, it's going to go all the way to the bottom. All right, cool. Enough of that. So this is our problem analysis. What do we need to know? Well, really, all we need to know is the very basic, which is acceleration is just a rate at which the velocity changes with time, and the velocity is just the rate at which the position changes with time, right? In this case, my position, I'm going to be using this vertical coordinate here, right? So this is going to be my x. I'm going to go ahead and say that my zero of this x starts right here. So therefore, here will be, call it 1 meter of the x. This would gonna be like 3 meters of x, 7 meters of x, and so on and so forth, right? So therefore, when it goes all the way down, that x equals d, d being the depth of the lake. All right. What else? We also know, what else do we know? We know that it takes 3 seconds, and we know the equation that governs the ball accelerating, and the acceleration is 10 minus 0.8 velocity. Because the acceleration is just the rate at which velocity changes with time, we can make this equal to the rate at which velocity changes with time, and I can use this to then, send equations around, and I'm going to have that, let's see, 10, let's do it this way, dv divided by 10 minus 0.8 v equals dt, right? So just rearranging that equation there. Why does that matter? Because now I can integrate this equation and I can find out how does the velocity change in respect to time. How the velocity changes. I can find an equation for the velocity specifically, I'm trying to say. And that will allow me to then calculate one of the things that we're trying to find out, which is what is the velocity when it hits the bottom of the lake, right? That's one of the things we want to find out. And then if I do that once again, right, after I found that velocity, so my game plan is I'm going to find this equation for the velocity. And once I have an equation for the velocity, it's going to be something here. I'm going to say, oh, this is, by the way, just the rate at which the position changes with time. I'm going to do the exact same thing again, integrate on both sides, and I'm going to get a equation for the position. And I'm going to say, okay, if this is an equation for the position, then I want a position when time equals 3, which is going to give me the distance d that I'm trying to find out. So that's the game plan. All right, so let's start here with this integration here. No, nothing special. It's just gonna have to do some substitutions. That's all. If you know substitution, you're gonna have to do it twice in this problem, and that's all you need to know. The only kind of, call it, information we have is that at t0, I'm calling this t0, my velocity equals v naught, which equals 16.5, right? And I'm using this, note that I'm using this on purpose because I would have the option of saying t0 was going to be when it was on this guy's hand, but rather what I want to do is I want to say t0 is when my x is 0, so that is when the ball is on the surface of the lake, because that's going to make my life easier, and because it doesn't matter. Okay, whatever you choose, as long as you're consistent, that will be correct. Okay, so how do I solve this integral? I have, obviously on this side here, I'm going to go all the way from time 0 all the way to time t. And over here, I'm going to go all the way from v naught, which is a 16.5, all the way to any v that I want. On the right-hand side, I'm going to get t minus 0, so that's lovely. T minus 0. But on the left-hand side, I need to do a substitution to be able to solve this. And what I'm going to do is I'm going to say 10 minus 0.8v equals u. And then I'm going to take the derivative of u in respect to v to see if I can keep everything as is. 10 is a constant, so the derivative is going to be 0. And then this guy here, the derivative is going to be minus 0.8. Minus 0.8. All right. And then that means that if I want to substitute it over there, then I need to, wherever I have dv, I need to substitute that by du minus 0.8 divided by minus 0.8. All right, so over here on the left-hand side, I'm going to go ahead and substitute here. I'm going to go from u naught to u for where I have the 10, where I have this is now u, this is what I'm calling u. And where I have the dv, I need to substitute that by minus, or just to keep it consistent, du divided by minus 0.8. Okay, this is a simple integral, natural log, so that's all good. So this means that this derivative is going to be minus 1 divided by 0.8 of the natural log of, how do I do this, u by u naught. So now I need to substitute it all back. This is equal to t. So minus natural log of v, what was it, u? I need to put u there. So u is going to be, so make it big, 0.8. And here I have 10 minus 0.8 v divided by 10 minus 0.8 v naught. That equals my time. Brilliant. All right, cool. It doesn't look pretty, but it is the right integral. And then to make it look a bit prettier, if I want to have this in respect to velocity, which is what I'm looking for, I can elevate all these to the e. And then if I do that, so I'm going to do e here, I'm going to do e here. And then when I do the e, obviously this guy goes away. And then on the left-hand side, I'm going to be left with, actually, before I do that, let me do one thing before. Let me go ahead and send this guy here, multiplying over here. And I'm going to go ahead and do that with the negative 2. I'm going to send minus 0.8 here, multiplying. That's going to make my life easier now when I do to the e. So again, to the e on both sides. So this e is going to eliminate this natural log. So really, this is just going to stay as is without the natural log, which is brilliant. And on the right-hand side, we're going to have e to the 0.8t. 0.8t, so that's 4/5. I like working with fourth is better than 0.8. Okay, let's just keep it as 0.8. All right, so now I have this on a better situation. What I can do if I want is send, obviously, this whole guy multiplying to the other side, and I probably should do that. And then I can also send this 10 to the other side as well. So one step at a time. So let's first send this one multiplying to the other side. I'm going to go ahead and copy. This comes over here, and then this stays the same. Times this. Let's make sure there are parentheses there so that we don't lose anything. And then we have that 10 over there. And so what I'm going to do is I'm going to kind of send this guy to this side as a positive, and then send this multiplication as a negative on that side. So I'm going to have 10 positive. So that's going to give me 0.8 velocity equals 10 minus e to the 0.8t times 10 minus 0.8 velocity, initial velocity. All right, so like I said, not pretty, but correct as far as I know. And that is an equation for the velocity. So then what I could do now, as of now, what I can do is I can substitute where I have t, can put 3, and where I have v naught, I'm going to put 16.5, and then I'm going to have a result for the velocity. I can go ahead and do that right now if I want to. Should we do that now, or should we do the distance first? Yeah, we could do that now. That'll be good. That's one way to do it. Okay, so I'll go ahead and do that now. So what I'm going to do now is substitute. So at t equals 3, v equals what? So to do that, let me change colors here. All right.